Now that we have finished all parts of Chapter 6, we are ready to run a review just to make sure that we have some good ideas on the material. You are proficient with what is going to be covered and ready for a test. All right. So I've gone ahead and sort of laid out the vocabulary here. These are not new words. Nothing should be a surprise. Remember, you are never tested on vocabulary, but if you don't know what the question means, you're going to have a hard time answering the question. So we are looking at the fact that work is the force times displacement, or the effectiveness of a force to cause displacement. We do measure work in the unit joule, and 1 joule is equal to 1 Newton meter. We've also looked at the work energy theorem. While you were not necessarily given this vocabulary word before, we have looked at the work energy theorem and we've applied it. We are looking at the fact that when you do work, you change the energy of a system. Or change the energy of an object. So we will look at the fact that forces from pushing and friction do work. Gravity in a system does not, but gravity does do work on an individual object. We don't need to get into too many nitty-gritty details on that, but the fact is when you do work, the energy changes. When there is no work done, the energy remains the same. Right? We do have the energy due to an object's motion is kinetic energy. Potential energy is energy stored for later use. We do talk about 2 types of potential energy, and that is the energy due to your height above the surface is gravitational potential, and then the energy due to a change in shape is the elastic or spring potential. Right? And when we look at both the potential kinetic energies of an object, we are looking at its mechanical energy. So that's that Ke plus Pe. So when we're looking at the fact that we're doing no work, all right, we have no external forces, the total energy remains constant. When work is 0, Ei is equal to Ef. Right? So that's the big sort of idea that we're going to end up using for problem solving moving forward. The last thing we covered in Chapter 6 was power, which was the rate at which work is done, and then that was measured in watts, which is a joule per second. I've gone ahead and highlighted the chapter equations. I would make sure that you have these in your notes that you are going to reference while you take the test. We are looking at the fact that work is equal to force times displacement times cosine of the angle between these 2 vectors. This is a big one, and I'm going to talk about that one more. We've also looked at the fact that work is equal to the change in kinetic energy. I've rearranged this equation slightly because the mass is going to be the same in both cases. I've actually factored the 1/2 m out of the final kinetic energy and initial kinetic energy formulas. Right, but it does mean the same thing as what we saw previously. We've already looked at kinetic energy is 1/2 mv squared, gravitational potential is mgh, spring potential is 1/2 kx squared. This is the spring constant, property of the spring, and this is the amount of stretch or compression. So how much did we squish or stretch that spring from its relaxed position? And again, we looked at mechanical energy is the sum of the kinetic and potential energies. We will be using G is equal to 9.81 meters per second squared for this test. I did give you some key ideas about angles. When your force and displacement are in the exact same direction, that angle is 0 degrees. When they are in opposite directions, that angle is 180 degrees. We will come back to these ideas again. Do want to make sure that when you are doing problem solving, your calculator is in degree mode. If your calculator is in radians for your math class, you will get the problem solving questions wrong. So please make sure that your calculator is in degrees. So I've gone ahead and broken this up into the big ideas of each section. The first one is the big ideas of 6.1. The big thing is that when work is done, when the simplest case, work is done when a force is applied to an object moves in the direction of the applied force. That means we have an object, it moves this way, the force is also applied in that direction, that same direction. All right, this is our simplest case for work done. The big thing to note, however, is the only force that does work is the component that's in the direction of displacement. All right. So if I have my object here, my displacement is here, I have some force that comes out like this. Only the portion of this that's going to be parallel to this. So if I were to break this down into its components, I have some piece that's here, some piece here. Only this piece right here of the force does any work. We could also look at the fact that if the displacement is 0, so is the work. That again comes from the equation work is equal to force times displacement. All right, if this is 0, this has to be 0. If more than one force does work, we can find this two different ways. We can find the work done by each individual work, or we can find the work done by the net force. The same process will apply. You'll get the same answer. And again, we went ahead and sort of refreshed the unit for work was the joule. So this goes into some reminders about angles. I get a lot of issues where if I have my object moving up, and my force is also up, people like to tell me that the angle between these is 90 degrees. Well, that is not true. 90 degrees forms this angle right here. This is what does 0 work. When they're in the same direction, we're actually going to have positive work. Right? So we can turn any of these pictures any which way. It's just a matter of what does this force look like compared to the displacement. How are they arranged compared to each other? Right? So anything in this range here is going to be positive. Right? Anything in this range that's not 90. If we're straight up or straight down, that's a 90-degree angle, that's going to be 0 work. This comes from that trig function. We have looked over and over and over again the fact that work is equal to force times displacement times cosine of the angle between those two vectors. So as we measure this angle, we look at what those values that come out get. If we do cosine of 90 degrees, we get 0. If we're in the same direction, cosine of 0 degrees is positive 1. If we're in the opposite direction, so anywhere on this side, we get a negative value. Cosine of 180 degrees is negative 1. So we're utilizing these ideas to sort of determine what the sign of the work is. Now, again, I told you that the positive, negative, and 0 for work does not tell you direction. What it does tell you is if you are changing how you are changing the energy of your system. You're either speeding your object up because it has more kinetic energy, you're slowing your object down because it has less kinetic energy, or you're not doing anything to it at all. You're making no change. So it's about whether you are adding energy, subtracting energy, or making no change to that energy. Right? So this brings us into what's going on a little bit more with kinetic energy and potential energy. Kinetic energy increases linearly with mass and the square velocity. Well, we saw kinetic energy is equal to, let me format this correctly, kinetic energy was equal to 1/2 mv squared. All right? For every small change in mass, we get a similar small change in kinetic energy. For every small change in velocity, we get a much larger change in kinetic energy because of that square term. We do already look at the fact that the total work done on an object is the change in kinetic energy. We also look at the fact that potential energy of an object is determined, apparently I can't spell, by the amount of work that is required to move it from one location to another. All right. So the fact that we did work to lift a book 1 meter off the ground, right? The work done to make it go that distance is the potential energy stored. Okay. Big idea number for 6.3 is we are looking at when the work is 0, the change in energy is 0. That means our initial energy is equal to our final energy. All right, remember this is mechanical energy. We're looking at the sum of potential and kinetic energies. So at any 2 points in time, our total energy will remain the same. All right, that's the big idea here. So I've gone ahead and included a little graphic here where we can see our gravitational potential energy here, our kinetic energy here, and our total energy here. This is our total mechanical energy. As when we started with all potential energy. Started with all potential energy here. As it moved, our potential energy decreased, and our kinetic energy increased. And we could see that those wiggle wobbled back and forth depending on how high above the ground that cart was. All right. So, and then of course, when it crashed into a wall, all the energy is gone. It was dissipated into heat and sound. The last concept was power. The faster work is done, the greater the power. Again, remember we looked at the fact that power was equal to work divided by time. We also found the fact that power was equal to force times velocity. Right? The faster we do the work, the more power is required. We did see the fact that the unit of power was the watt, or a joule per second. We also see a common unit for power is the horsepower, HP, and this is the conversion factor for that. So while these are exactly the same, we could take a look at the fact that work is done in both particular cases. The same amount of work is done in both cases. We could also look at timing these. If I were to double how quickly this one plays, right, so it shoots up in half the time it did, we're now going to see a much larger power than we do here, right? So power is equal to work divided by time. As time decreases, power will increase, right? So that's a big sort of overlying idea. All right, that concludes the Chapter 6 review of the big ideas. You will have practice problems to work on in preparation for the test. Please reach out with any questions. We can schedule time during office hours.